Hi there. Today we'll look at Language Models are Open Knowledge Graphs by Chengwang Wang, Xiao Liu, and Dawn Song. This paper, on a high level, proposes to construct knowledge graphs, which is a structured object that's usually built by experts, either fully manually or semi-manually with heavy human involvement. It proposes to construct knowledge graphs automatically by simply using a pre-trained language model together with a corpus to extract the knowledge graph from. The cool thing about this paper is that there is no training involved. So there is no model that learns how to construct a knowledge graph. The entire knowledge is simply extracted from running the corpus once. So one forward pass through the corpus through the pre-trained language model. And that constructs the knowledge graph. So that's kind of the core message of this paper. They say this paper shows how to construct knowledge graphs from pre-trained language models without human supervision, and it turns out the way they do it, it works pretty well on kind of standard knowledge graph construction benchmarks. So that's the paper in a nutshell. We'll go through all of this, including I have a bunch of criticisms, but it is a preprint, remember this. And yeah, so usually I'd say at this point, if you like this content, don't hesitate to share it out and so on. Today we're going to try something different in 3, 2, 1. Stop. It's sponsor time. This video is sponsored by Tab9. Tab9 uses deep learning to help you write code faster. What could possibly go wrong if you do that? No, I'm joking. Take a look at this piece of code here. I was trying to refresh some elastic indices, and as you can see here, all I said was could, and Tab9 completes it to could not refresh, because above I was trying to call a refresh method. This is something that I haven't seen any other completion engine do yet. Compared to a regular coding engine, Tab9 is trained on lots of open source projects, and it combines this with your code, and it predicts what you want to do compared to predicting what's possible, which is what a classic engine does. Tab9, it uses a GPT-based model, and it downloads that model onto your machine. So the code never leaves your machine. There is an opt-in feature where you can run that in the cloud, and that will just give you a bit of a better beam search and better quality predictions. And it saves you a bit of RAM. As you can see, I myself use Tab9. I just have it on by default, and I'm pretty happy with it. I use it through COC, integrated into my NeoVim, but you can also get it in Sublime, Atom, IntelliJ, VS Code, even like Jupyter notebooks, and you can use it together with classic completion engines. So you can really get the best of both worlds. So whenever you see me code in a coding video, look out for this TN marker next to the completions. That's the completions by Tab9. It doesn't only work for Python, it actually works for pretty much any programming language that isn't completely obscure. If you go to this link within 72 hours of when this video is released, you'll get 3 months of Tab9 Professional for free. The professional version removes the project size limit of the free version, and it also gives you access to that sweet cloud inference. After the 3 months, you're automatically kicked out of the pro version. There's no auto sign up. There's really nothing to lose. I mean, the only bad thing here is that Tab9 itself is written in Rust. Ugh. If that's the worst thing about an offer, it's a pretty good deal. Again, I use this myself, and I'm pretty happy with it. So again, if you sign up at tab9.com/promotion/YannickCulture, within 72 hours of when this video is released, you'll get a free 3 months of Tab9 Pro, no strings attached. And now enjoy the video. Thanks. All right, I hope that was fun. Let's get back to the paper. Let's get into the paper. So first of all, what is my first criticism of this paper? The title. There are some disturbing trends in the last few years in machine learning papers, and the disturbing trends can be maybe encapsulated with the phrase "is all you need." So people have sort of, since attention is all you need, since this paper, people have discovered that if they just append this to whatever their paper is about, then the paper will get much more notoriety. And the same thing, I think, is a bit at play here with the R, because in recent times, we've kind of seen a bunch of papers that show equivalences between models, such as a famous example is that the transformers are Hopfield networks in some regard, and these papers are pretty cool, right? Even if the two things are not exactly equal all the time, if you can say, look, there is a setting, there are, under these assumptions, under these settings, in this situation, these two models actually are the same. That's a pretty cool recognition, a pretty cool thing to show. And it's very useful for academia and practice, I believe. However, I believe the R keyword, the is keyword, should be sort of reserved for when two things are equivalent. Whereas here, in the very first, at least they're honest, right? In the very first sentence, they say, well, we show how to construct knowledge graphs from pre-trained language models. So essentially, they're going to use a language model to approximately construct a knowledge graph. And they're also going to use a bunch of other auxiliary models that come all pre-trained, but still they do not show an equivalence of language models and knowledge graphs in this paper, not at all. So I see that you can get somewhere with these titles, but maybe people will be disappointed kind of if they read the paper, which it is actually a cool paper, believe me. All right. So, as I said, what we have usually is a corpus, okay? A corpus is simply a bunch of text pieces. You can think of maybe just the text in Wikipedia, okay? Here, the Wikipedia page about Bob Dylan. Bob Dylan is a songwriter, was awarded a Nobel Prize, signed Albert Grossman. These are easy sentences, right? There can be... Sentences are usually larger and longer and so on. And what you want to do is you want to extract a knowledge graph. So the knowledge graph has two distinct things. It has entities, and one entity here would be kind of Bob Dylan, songwriter is an entity, Nobel Prize is an entity. You can sort of think of them as nouns, okay? And then the second part in knowledge graphs are the relations. Here, occupation, sign, award received, and so on. So the relations connect to entities. There's always what's called a head of a triple, so a head of a fact, which in this case is Bob Dylan 3 times. Then there is a tail, which is sort of like the object of the verb, and then there is the relation, which is described by the verb. Now, here you can see there are two stages of constructing such a knowledge graph. Any system that does this probably goes through these two stages. So first you extract a set of candidates, which it's not the knowledge graph yet, because these are still strings, right? You extract a bunch of string triplets, as you can see here. And as we said, as the sentences get more complicated, it gets more and more difficult to extract these kind of triples. And then the second part is that you need to map it to a scheme, to a schema. And these schemas are usually defined by humans. So here we're still going to rely on humans to define the schema. So there is one list that says entities. And the entities, the entities are listed, okay, by the humans. And at some point it says Bob Dylan, and it has a bunch of mentions of Bob Dylan associated with it. And it has a clear ID. In this case, you see the ID is Q392 in that knowledge graph. And the system not only needs to extract these facts, but then also map these facts to the correct entities. Map these facts to the correct schema entries. This second stage right here is a bunch of standard tasks, so especially mapping something like the word Dylan in its context to this entity Bob Dylan, which you can think of it as like the Wikipedia page of Bob Dylan, right? That's how these systems usually work. That is a task called entity linking, okay? entity linking, and similar tasks exist for like the relation awarded, mapping this to award received to this. So maybe there's some kind of a dictionary entry, award received, and what it means, and a bunch of examples, and you're supposed to map this to that. These are standard tasks, and the system that we are going to look at right here is not much concerned with these tasks. It simply uses pre-existing methods to do these things. So the system we're looking at today does this first part right here. It takes text, okay, this is text, and it comes up with these candidate facts about the text. Whether and how this is then mapped to the schema, that is a different question, and there are pretty cool things in this paper about this step, but we're first going to look at the first step and then at the second step, all right? So how does this system do this, and how does it do it? There have been machine learning models before, but being machine learning, they all have like some sort of a training corpus where you have kind of the facts as a training set, and then you have a separate set of facts as a test set, and you try to learn from the conjunction of the text and the training facts how to extract facts. Not this system. This system simply uses a pre-trained language model. So what's the reasoning? The reasoning is the following. We used to think that we could do NLP probably best with having a knowledge graph, right? With having this set of very structured data. We can answer something like, what's the age of Barack Obama's wife? And then you could go to the entity of Barack Obama, you could look at the relation spouse, you could go to Michelle Obama, you could look up her birth date, which would all be structured information in this graph. So you could sort of answer questions like this, and search engines like Google and so on, they have this built in. So there is kind of a knowledge graph entry sometimes when you search an entity in Google that pops up. And these have been very useful to answer questions like this. However, in recent years, language models have become better and better. Things like BERT or GPT-2 have become better than these expert systems, let's call them, at answering questions. By the way, if you want to hear a very, very cool and solid argument of where these kind of expert systems, where this kind of structured human annotated or maybe extracted information can still come in natural language understanding, I would recommend the Machine Learning Street Talk episode we had with Wally Saba. Extremely interesting person, and I can recommend listening to that. This should be out any day now if it is not already. So the language models have become better and better at these tasks without having this structured information. So the hypothesis is maybe these language models can already contain the information that's necessary to construct these structured facts, because the structured facts is what we, let's say, should use to answer these questions, because we feel that structured information is better than unstructured. The language models are pretty good at these tasks, so maybe we can get the structured information out of the language models. So that's what they do. They say the contributions are as follows. We show how to construct knowledge graphs from pre-trained language models. The knowledge graphs are constructed with a single forward pass of the pre-trained language models without fine-tuning over the textual corpora. I think this is kind of a very strong point about this paper. And it also shows that if you're some PhD student somewhere and you don't necessarily have the resources to train the next GPT-3 model or even fine-tune it, there is still research to be done. Simply, if you have enough resources to forward pass your data, which is often much fewer than to train one, you can still do very cool research. I think this paper shows this explicitly. Okay, this helps researchers explicitly understand what the language models learn, bridging the deep language model and the knowledge graph communities through enhanced model transparency. Okay, they say we propose an unsupervised two-stage approach, MAMA, M-A-M-A, which stands for match and map, to first match the candidate facts in the corpora with the knowledge stored in language models. That's the first step we looked at. Then map the matched candidates' facts to both fixed and open schema to produce a knowledge graph. And then they say they produce a new type of knowledge graph, which simply is that the facts, sometimes the facts they extract, they can't really map to a schema entry. And we're going to look at that because I think a bit critically of this. They say, namely, the open knowledge graph consists of mapped facts in the fixed schema of existing knowledge graphs annotated by humans, and the unmapped facts in the open schema that are new in the reference knowledge graph schema. So what they claim here is that their system is finds these new relations that don't even exist in the schema and is able to uncover, kind of build new additional schema entries. And they call this the open knowledge graph. I'm a bit skeptical of this, as we're going to see. So the first step, how do you come up if you have a sentence? And this is a very poor example, I feel, honestly, to do this. I get it must be short, but it's a poor example. But stay with me. So you have this sentence, Dylan is a songwriter, and you would like to extract a fact from this. The paper is not really written clearly on how, it is, you can parse it out, but the description is kind of distributed. So step one is run Spacey. Run Spacey. This is a standard kind of library for NLP to extract noun phrases, or they call them noun chunks, okay? So step one is there's nothing to do with the language model. It is simply you want to find the noun phrases in here. The noun phrases are Dylan and songwriter. Now, these noun phrases now define your head and your tail of the fact. So you already have two things, right? So the entire task of their method they're proposing is, so the step one is run Spacey to find the head and the tail of facts. Step two is question mark for now. Step three is going to be use the entity linking system and the relation linking system to construct the knowledge graph. Okay? So step one is steal underpants, and then step three is profit. So what's step two? Step two is, obviously, step two is where their system comes in. Step two is, here is the head, and here is the tail in the text. Somehow, where in between, there might be a relation, and we need to figure out where that is. Okay? So how does this method figure it out? So you already see the assumptions here are very, very restrictive, right? So you use Spacey to extract basically noun phrases, which means you're probably already going to miss a lot of things that are not recognized as noun phrases. And they also say that Spacey's annotations are sometimes error prone, and that's why they miss a lot of things. And then secondly, the assumption that the relation must be in between the two things textually. Now you can run the algorithm forward and backward, but still it must be in between. And it must sort of be encoded, let's say, as a semi-accurate string in there. I guess then that's up to the relation linker. But already these assumptions are super constraining in the kind of things you can find. And you'll see in the experiments that their biggest flaw is that they have a very, very low recall. I mean, so do all the systems on the task, apparently, but they still have a very low recall, and it's because they constrain their problems so much. I'm going to guess if they wouldn't constrain their problems so much, then they would have maybe a better recall, but their precision would just plummet because these things, if you let them run wild, they just over-extract. So basically every verb in every sentence is going to be a relation, right? So like, I ate a banana. I ate banana would be a triple, not necessarily a really valuable entry in any knowledge graph, though banana has a lot of carbs, so I would want to know about that. Okay, so you see that the task is now reduced from building knowledge graphs to simply, given a head head annotation, head piece in the string, span, and a tail span, extract any span in between the head and the tail that describes the relation between the head and the tail. So the way this algorithm does it, that's where it uses the language model. Okay, so here it's going to do something that is going to be similar to dynamic programming. If you've seen kind of the dynamic programming kind of search algorithms, let's say string matching algorithms and so on, this is going to be sort of similar in that what we're going to do, we're going to start from here, from the head in the string. There could be text before it, right? We're simply going to locate the head, Dylan, right here, and going to start. Then we're going to look at its attention matrix. Now the attention matrix is, we're going to cross out here. The attention matrix, I've done many videos on attention. The attention matrix basically in a sequence means how much each token attends to each other token, right? How much information is kind of sent from each other token to this token right here. So this up here would be the query, and these would be the keys. The attention matrix specifies that. So since we locate things between the head and the tail, what we want to do is we want to cross out, we want to disregard everything that's kind of behind the query and only look ahead in the sentence. Okay, so that's why the sum of the attention matrix here is crossed out. As you can see, these are the x's. This is exactly because we only search in one direction. So from the token Dylan, we can look at three things. We can look at is, a, or songwriter. And the question is simply, where do we go next with this algorithm, right? There's no interpretation yet. It's simply, where do we go next? And the where do we go next is simply answered by just taking the highest scoring thing in that column of the attention matrix. Look at the attention column of the token Dylan. I take the highest scoring one. That's 0.3 here, is higher. Okay, then I go to 0.3, and that means is gets into my candidate fact. Okay, and once I put is into my candidate fact, I then go to is. So the next thing I do is I go to is. And then I again look in the corresponding attention column, and I see what's now the biggest entry here. And the biggest entry is 0.4, which is songwriter. And you can see here, now we skip the A. That's how we leave out some text, okay? By skipping it, basically. So you can see that this can create artifacts, right? This can create like kind of holes in the middle and so on. But we skip A, we go directly to the 0.4, and then we discover, the 0.4, that is our tail. So now we put our tail into here, and since our tail is the last word, we can stop the algorithm. So there is no need to go on, even if there were text behind the tail. As soon as we are at the tail, which we already know, right? We're given the head and the tail, we stop. All right, so we simply go forward with always the biggest entry in the attention matrix until we reach the tail. That's the algorithm. It's described here, but it's kind of described in this way where it has these actions like start, yield, and like this. Maybe I'm not understanding something, but it seems completely unnecessary to kind of describe these actions. And it basically start the search from the head. The head is added as the initial candidate and so on. Then in yield, it sometimes says with the largest score from the attention matrix is appended to the end to yield the new candidate and so on. But still, and then stop, we stop. And the algorithm description here, it basically just says while we're not done, if it's not the stop action, we continue. It's sort of, it doesn't tell you anything. Like this is a super unclear description of this algorithm. Basically, the whole logic that you would want to know about is here in this action manager, right? So the action manager that gives you the action is doing the actual logic of figuring out which token you should do next and where you should go next and so on. This is nowhere in the algorithm. The algorithm just describes beam search. So you can do this a little, the little more sophistication that comes in is that you don't do this deterministically, but you actually do it via beam search, okay? But you can just generalize this, all right? So the description is a bit floppy with the whole actions and action manager and whatnot, and not describing, the only thing they don't describe formally is how actually to select the next token, which is basically the entire kind of meat of the algorithm. In any case, this is something that confuses me right here. So fair enough, they say here we take the attention matrix and we cross out these X's, all right, but they say they can take things up here, right? They can take things like BERT, and as I said, fair. BERT has a full attention matrix, everything attends to everything, but they can also take things like GPT-2. Now, GPT-2 is an autoregressive language model. That means that in GPT-2, if you look at it, then you produce each token one after another, which means that when you produce, so each token, when you train or when you evaluate, even each token can only attend to the things in front of it, right? You see the problem with what this thing requires. Oh, this is also the same. Okay, let's do that. You see the problem with this method is the exact opposite. Each token attention matrix is deleted such that only the entries ahead of it are in the attention matrix, right? You don't actually get GPT-2 to give you an attention matrix that looks ahead because it only ever looks behind. So maybe what's happening is that the query and key matrices are switched up in some way. In that case, when we want to interpret the algorithm, the way they write it down is, if I am at a particular part of what I think is the relation between the two entities, how am I going to find whether or not there is more to the relation, right? It could be a multi-word relation, like has a child with, or I don't know. Can't think of any multi-word relations, or whether we kind of are done with the relation and go to the tail. What this thing is saying is that we should look at the language model. So if this is really how it is here, and you are at the word is, what you want to know, if this is BERT, if this is a BERT language model, what you want to know is, if I were to cross out is, if I were to delete this word, which other words in the sentence right here that are ahead of me are very, very informative to predict this particular word. And that's kind of the query style. And, if the answer turns out to be songwriter is quite important for that. Maybe Dylan is too, but we only look ahead. If it turns out the word A is not as important as the word songwriter, right? Because songwriter, it gives an indication that there should be is, because songwriter is kind of a profession and there's a person in front of it. We don't look at that, but the attention matrix would have that in mind. That's valid, right? So that's how this construction is made. However, if this is the key, we have to think of the other way around. If we are at is, we look ahead and say, if I were to delete the word A, could I reconstruct it? How well could I reconstruct it from this word is? Or if I delete songwriter, how well could I reconstruct that from the word is. I think both are, there is interpretations probably for both of these methods, but what I want kind of to convey is that none of these things are really amenable to constructing a knowledge graph. It's quite interesting that this stuff actually works, because all it asks is how well does one word inform about the presence, or how well can one word predict another word. And from that information, we construct this knowledge graph, which probably is a testament to the fact that knowledge graphs maybe aren't so much about knowledge if you extract them from a corpus, but more about grammar. I would think that's a thing that goes on here, because these language models are a lot about grammar, right? A lot about how different words appear together frequently. So given that songwriter, it's kind of a mix between grammar and basic word knowledge. Given that songwriter is kind of an object here, the word is, being the verb, is probably quite important for it. And that's exactly, these triples, they always appear a bit like kind of compressed sentences, and which are very grammatically relevant. So I'm not buying this hypothesis that there is much knowledge in these language models, and that's why this works. What I much rather think is that they are really, really, really good at kind of grammar and statistical association between words across the language, and that's why they can extract these candidates' facts so well. Okay, so that's what I think about the algorithm. They do constrain it some more, as if it doesn't already have enough constraints, but they all make sense, okay? So they say the matching degree, which is simply the sum of all these attention matrix entries that we've encountered during our search. So all the ones we didn't skip are to counted together, are the matching degree of this triple. The matching degree must be above some threshold. That's the first constraint, because, so they give an example right here for the sentence, Rolling Stone wrote, no other pop song has so thoroughly challenged artistic conventions. And the extracted candidate fact is Rolling Stone wrote pop song. Right? Again, you can kind of see here, it's mostly going into grammar-ish. So Spacey extracts Rolling Stone and pop song, and the language model here extracts like the only verb in between, wrote. So yeah, to kind of limit the matching degree, to say it must be at minimum kind of some number, it makes a lot of sense, because if the matching degree is high, that means, if we go by this attention matrix, it means that these words that are in the candidate fact, they kind of, as themselves, they follow from each other. So the language model thinks that wrote is a very good follow to Rolling Stone, and pop song is a very good follow for wrote, or the other way around, depending on which way the attention matrix is. But that's kind of, the language model thinks that these words together make sense. In the context of the sentence, of course, like in the context of this entire sentence. So, as I said, it's sort of think of it as a bit of a summarization paper, but with more constraints. Constraint number 2 is that the frequency of R is above a threshold. So the relation itself shouldn't be too specific. It actually should appear a bunch of times in the corpus. So what you do is, you go through the corpus once, extract all the facts. My pen just dropped. You extract all the facts, all these candidates, and then you kind of count them and go through the candidate facts again and delete all the ones that are below a certain thing. People usually do this with things like stop words or rare words and so on. It's pretty standard, makes a lot of sense. And constraint number 3, relation R is a contiguous sequence in the sentence. Okay, so they have an example here from the same Rolling Stone wrote challenged conventions, which the language model would like to extract, because again, these, in the context of that sentence, these words sort of, they jump to each other in the attention matrix because you can predict them from each other very well. But they say this must be a contiguous sequence. So what I said before, I said this could happen. With this constraint, they exclude it. Okay, so for the second part, where they actually have to map a candidate fact to a fact in the schema, as I said, they use kind of pre-made solutions, entity linking and relation mapping with the schema. I won't go into this, except to say that whenever they find a match, they say that this is a mapped fact. Whenever they don't find a match, they say, this is an unmapped fact. Okay, an unmapped candidate means that at least one of H, R, and T is not mapped to the schema. There are two types. Partially unmapped facts is where some are mapped, and completely unmapped facts indicate that all H, R, and T are not mapped to the schema. Okay. For example, Jacob was a registered Mennonite. Now here, they say they have these different facts, and it's a cool thing if a model like this can actually come up with new facts. Not only new mapped facts, which is something you would expect, right? If humans provide some kind of a schema, then build a knowledge graph, this is never complete. So if you can automatically kind of fill in missing facts, that's very, very cool. Though I would say humans, if you construct knowledge graphs, humans should probably also build kind of like negative connections, saying like, yes, it is conceivable that Elvis was a vegan, because a lot of texts talk about it, but in fact it is explicitly not. I don't think that's what we have in the knowledge graph so far, but it would be cool if this model could fill in new facts, yes, to the schema. It would also be cool if it could uncover completely new relations that hadn't been considered by the human makers of the knowledge graph. Like, if the knowledge graph itself is incomplete, the schema is, same argument, the schema is probably also incomplete. This paper is sort of trying to sell their system as something that can do that, and I believe that to a degree, but also, Jacob was a registered Mennonite. Okay, now, maybe I'm completely wrong. From the sentence, Jacob was a registered Mennonite in Amsterdam. I might be completely wrong, but Mennonite is a religion, I think. And I'm very, very sure that any of these knowledge graphs with the schemas that they have being in a religion or being of a certain faith in their relations table somewhere. And I'm also pretty sure that Mennonite large enough that would actually appear as an entity. Maybe Jacob not, right? Maybe Jacob is an unknown Jacob. We don't know who Jacob is. But this seems more like a failure of the entity linker and relation linker than an uncovered new relation or an uncovered new entity. So yeah, take this stuff with a grain. Now they are very honest about this, but just to say that that's probably what happens most often. So here you can see the graph for Bob Dylan constructed from the Wikipedia pages that are kind of, they say around the page of Bob Dylan. So I'd guess 1 or 2 or 3 hops away, something like this. And you can see the blue stuff is stuff that we already knew, so that the humans also found when looking at this. Then yellow stuff, I believe, is either new relations. So whenever things are annotated, it's a new relation in the schema. So you can see this is an entity in the schema because it's annotated. This is a relation in the schema, but the arrow is new. So the humans hadn't yet extracted the fact that Bob Dylan was a member of Artists United Against Apartheid. Then The yellow also sometimes means that there is a new thing. So here, tour with is a relation that's extracted that is not in the knowledge graph yet. Also this one. And it's pretty cool, right, that you can extract these things automatically. There's a lot of yellow stuff here, which means there is a lot of new information that this extracted, and a lot of this new information is actually mapped to the schema, right? Bob Dylan, residence in Duluth. I don't know how to pronounce that, by the way. Yes, so that's fairly cool. They do some of these tasks, of these knowledge-based tasks. So in these tasks, what you'd have, I believe, what you'd have is always, you'd have like a head and a relation given. So you have a document, and you are given a head and a relation, and you're asked, what's the tail of this, right? And then you ask the system, and the system will tell you. So you have these baselines, and these baselines, I believe, they are specifically made to extract these knowledge representations. They might even be trained. I don't know that, but you can see that the MAMA, even the smallest one here, beats those by quite a bit. Now you can see that the recall is significantly lower than the precision, which is a direct result of how many constraints on the system there are, and tells you sort of what going forward, what the improvements can be. So they analyze a lot of this, and yeah, so a first recognition is that larger and deeper language models produce knowledge graphs of higher quality. BERT language models outperform GPT-2 language models under similar model sizes, which is interesting. Is scalable to larger corpora, which again, as we said, you don't need to train it. And larger corpora embed more complete knowledge graphs, which is something we would expect. The other interesting part is the unmapped facts. So the numbers you can actually compute only for the mapped facts, right? Because that's where you have data. Humans produce the knowledge graphs from this. That's what you can compare with. Now the unmapped facts, they say, they analyze. We turn to study the quality of the candidate facts that are not mapped to the above referenced knowledge graph schema, but are in the open schema generated by MAMA. We manually judge such unmapped facts generated by our best method from 100 sampled documents in Wikidata and TAC KBP respectively. So they go as researchers, they look at these things and they judge them whether or not they're true given these documents in Wikipedia. They say the quality of unmapped facts is verified. So the claim is that they've looked at them and they are good. We find that 35.3% of the unmapped facts are true on Wikidata. We find that 83.2% of those true facts are partially unmapped facts. For example, Bob Dylan tour with the Grateful Dead. And yeah, here is if this really isn't in the schema, right? This is a nice relation that you might think humans would miss, because touring with someone is not the first thing that would come to mind if you had to come up with a bunch of relations between entities. But it is something that is regularly useful, regularly used for musicians. So that is an application where certainly an automated system can even extend the schema, right? Whose relation is not within the schema of Wikidata, while both head and tail are in the schema. The remaining true facts are completely unmapped facts. For example, this Jacob was a registered Mennonite. And they also say accurate entity detection is desired, where they say a lot of the errors are due to Spacey detecting wrong, incorrect entities, or due to incorrect or missing entity linking by those systems. The rest errors made by MAMA are incorrect relation phrases, such as uninformative relation phrases. For example, Bob Dylan made and his breakthrough. Well, what can you do? What other verb would you put there? Yeah. But okay. we're going to look at a few last things right here. They have a bunch of experiments right here, where they show, you know, the beam size has an influence, this constraint number 1 and number 2 that we looked at has an influence, right? So you can tune these things a bit. What is interesting here is they try to look at either the attention matrix of the last or of all the layers. And interestingly, the system performs better if you only look at the attention matrix in the last layer. Now they reduce that attention layer because there are multiple heads using max or mean. You can see they perform similarly, but it is interesting that only the last, and they argue in the text that we know that the last layers kind of have higher level features than the lower layers, but I recall there are multiple papers, like I've done videos about them, what does BERT learn and so on. I think even something in conjunction with lottery tickets and so on, that show that in a transformer at least, I think it is the middle layers that encode the most kind of semantic knowledge. Because the lower ones, yes, they are for kind of low-level features, but the upper ones, they are again for low-level features because the task right here at the end is to predict an individual word or token, right? So you'd expect that the features in the attention matrix there go back to kind of sort of more grammatical features and so on, and that the highest level features are actually somewhere in the middle. I don't know if they only tested like all versus last, in which case, yeah, I believe that. But if they tested each one individually and it still turned out that last is the best, that would kind of add to my hypothesis that what happens here is more kind of a grammatical effect of extracting this correct candidate verb in between the head and the tail. All right. So that's kind of gives more weight to my hypothesis. Like, so to repeat, my hypothesis is that it's kind of a grammatical thing that's going on here, because the only task of this model is basically to find the correct string span for the relation between head and tail, because it's already given head and tail. And from the text, their hypothesis is more like the language models have a lot of knowledge built into them, and we can extract that knowledge. They make it sound like the language model has this semantic knowledge in them. Okay, so let's look at a bunch of mapped facts right here. You can maybe check out a lot of them yourself, but we'll just look at like one in each category. Blah, blah, blah's male, yada, 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 is in worse shape. However, Klaus told press conference at the western city of Essen where yada, yada, yada. And it extracts this company and it maps it to the city of headquarters. Maybe they leave out some text here. What I want to get to is the unmapped facts. Where are the unmapped? Mapped facts. To just kind of show you mapped facts, unmapped facts. Okay. So the unmapped facts, what I feel, and you can judge for yourself, please. What I feel, just to pre-bias you before we look at them, is that a lot of times simply it extracts things it extracts things that are not, it simply can't assign things, right? It's a failure to assign. It's not a new thing, because in these schemas, like you haven't seen the schemas, but you kind of get a feel. Which is the last table? You kind of get a feel of what contains in it. So maybe get a feel for what. Okay, Ernst Haeckel was born 16th of February 1834 in Potsdam. Okay, so the extracted thing is Haeckel was born on 17th of February 1833 in Potsdam. Okay, so that it maps to this is in the knowledge base schema. This is in the schema, but was born on 17th of February 1833 in is simply a failure of the relation linker. he was also a pacifist until the First World War, yada, yada, yada. And then Ernst Haeckel, and then was and a pacifist are both not in the schema. Now, maybe pacifism isn't in the schema, maybe, though I would guess pacifism has a Wikipedia page, so it must be in the schema because it's a Wikidata. But was, as, you know, the relation here would something be like a political leaning or something like this, which is certainly in the knowledge base, right? Then you have things like Haeckel was awarded the title of excellency. So you have correctly, Haeckel, again, recognized, award received is in the schema, nice, excellency as a tail. And excellency, you know, what do you want? Like, this is not a fact, right? This is the award or the title of excellency would be kind of the thing. So this is a failure of Spacey. So again, I've seen little facts here that would actually be of a genuine addition to the schema that should be considered. And I absolutely believe that the schema is incomplete. Don't get me wrong. At 100%, the schema is probably less than 1% of what it should be, right? If we did a thorough job. I just don't think that this system here is a good, like, I think that the things that this system comes up with mostly are simply failures of its subsystems rather than genuinely new entries to the schema. That's different from when it genuinely discovers a new mapping between already established things. For example, Pauline Baines educated at this college, right? So these are new facts, all fit in the schema, and the system might be very, very nice for that. All right, so that was my kind of estimation of this paper. I hope I didn't rag on it too much. As I said, it's very cool work, actually. I look at this appendix, it's giant. Go look at it, check it out, please. Tell me what you think about it in the comments. Any feedback is welcome. And I will see you next time. Bye-bye.